Good afternoon, everyone. I'd just like to introduce myself. My name is Mike Cagle, and I'm a member of the engineering marketing team here at Buckley Associates. Before we really get started, I'd like to say a couple of words here. To start, thank you, everyone, for participating today, for taking some time out of your day to spend with us and learn about transform your single-phase AC motor into an intelligent ECM. It means a lot of us here at Buckley, and a lot of effort goes into the planning of these webinars, and we're very happy that you see a value in the services we are providing to the engineering and contractor community here in the Northeast. Our presenter today is Art Durham. He's the co-founder of Acolytic, and he's got 12 years experience in engineering, marketing, and management. Holds an undergraduate engineering degree from Stevens Institute of Technology. Attended graduate program at Vassar College and State University of New York. Also on the call with us is Pradeep Haldar. He's the co-founder of Acolytic as well. He holds a PhD from Northeastern University, an MBA from RPI. And they're going to be giving you some really good information today. So kind of sit back and enjoy yourself. And we appreciate their time giving this presentation. So there are quite a few people on this webinar. All of you are muted during the webinar just to keep things running smoothly. What I ask, if you have any questions, just go ahead and write in the question that you have, and every so often we'll interrupt and answer those questions, and to make sure to get the answers that you have, that you need. So now that we get going, I'd like to hand the presentation over to Art, and I appreciate your time, Art. Thank you.
Thank you, Mike, and thank you, everyone. As Mike mentioned, it's kind of a team effort, Buckley and Pradeep and myself. So Pradeep is going to actually be moving the slides as I discuss them. However, as Mike also mentioned, we strongly welcome and encourage any questions or expansions you'd like. I have a tendency to ramble, but so I don't want to linger too long. But please feel free to ask questions. I'll pause every so often and allow you to do so. So to start off with what we're really discussing today, Electric is an Adaptive Photonic Controller. And you'll notice there that little picture on the right there. That's a 4x5 blue box that in essence is the product that we're going to be talking about. It's an aftermarket ACC-ECM Plus. And we'll explain some more as to why it's been given that name and description. Next slide. We're primarily focused on light commercial, high rises, commercial. The unit, as we mentioned, is a small end user unit, but the HVAC industry is just one of the many places that technology fits. And in our discussion today, it's going to be mostly for non-single families, but more multifamily high rises. And why there? Because generally when you're trying to lay out a solution, an engineering HVAC solution, you see on the left there are a myriad of suppliers, manufacturers, competitors, and a litany of options as to how to heat and cool an occupied space. And within those options, there are sub-options and more options. And here are just some examples of like all the features, functions, models, part numbers. It's a potpourri of stuff there that's like can overwhelm. So what our goals is that we're trying to say, can we provide the industry an opportunity to address the needs of the end user, but simplify these choices, but yet enhance your options? And that's what the goal and we think the achievement of the ACC Plus is. Next slide. And why? I mean, when you really cut down to it, the simple thing is we're trying to give some indoor thermal comfort. And we see this nice photo here of a family enjoying that. And most people usually think of temperature, but we know today now there are other factors that really dictate how well that comfort is. The indoor air quality, humidity, the filtration, and we know now more so, adequate ventilation. And we have highlighted there clean, fresh air, because always so-called outside air does not fit the category of clean, fresh air. You see the asterisk. We're going to address that, what that means. And also, ideally, we want to do this without wasting a lot of energy, an ideal, preferably, less energy. But satisfying the room occupant comfort is really the overall goal of what we're about. Next slide. So we're going to kind of zero in on a typical unit that's a water source heat pump fan coil. And in this case, you see it's a single riser type unit. And the individual unit has its own ability to add supplemental heat and cool to that pipe that's there, providing the extraction of that heat, or cool, extracting the heat and providing the cool. Next slide. So that individual unit is usually not one or two or even a dozen. Generally in those high rise, you can literally have hundreds of them. But when you do, you start running into some by the ways. These individual units may operate on their own, but they're part of a whole, and that whole impacts the individuals. And what we're highlighting in the middle here is an example of looking at a microcosm of just two units. The water entering at 80 degrees on the unit on the right goes through that unit. As it does, it's going to extract some of the heat energy in that room, transfer that heat energy to that fluid, pass it out at 82 degrees over to the next one, which now gets 82 coming in. It's going to extract heat from the room, add it to that source of water or refrigerant, send it out at 84. And if you look over to the right and you imagine this now being replicated dozens of times, the point is that the picture on the right there, those units on the lower right, or upper right, I should say, versus the upper left, are not seeing the same thing. And yet they're operating in the same way. And let's go on to the next slide. So we kind of zero in on the left. We're talking about one of those units with heating, and it's the elements in there are a fan for distributing or moving the air into the occupied space, and supplemental heating in this particular case with a compressor and a heat pump. But you'll notice there's these blue arrows on the left that's returning air that's going to go over that coil, which is then going to get warmed up. And as it does, it's going to be blown out through the top and out. However, what happens to that air is going to be supplemented by the water that's running through the water source heat pump. So as we saw, that pipe on the right there is going to see an incoming water temperature that's different than the outgoing water temperature. And on the right, you see a similar thing. But what's affecting that water temperature? It's the return air in the blue. It's the amount of air that's being pushed across it. It's where it is in the loop. It's the moisture content, how much outside air. And when you start looking at it, there are numerous things that interact with what's happening inside that little box. But as far as control and function, you really just have an on-off usually of the heat source. Open valve or open source of heat or cool, and you have a fan that is usually moving at 1 or maybe 2 fixed speeds. So what we're highlighting here, that there could be a significant benefit if each of those units had the ability to recognize the conditions and affect some adapting of those conditions. Next slide.
Turn up here.
I think we got a little background noise there. This is kind of looking at a unit that's now added some added smarts. In addition to the fan and heat pump, it also has an ERV system that is bringing in outside air and conditioning. And
Mike, can we mute everybody
today I'm
else?
getting a lot of background noise.
Is everybody
Can you hear
muted,
me?
Mike?
Yeah, everybody's muted. I apologize, Art.
Yeah. Okay. All right. As long as I'm being heard okay, I guess it's all right. So looking at this, you see there are a number of things. Now we've added in outside air. The outside air has to be conditioned by this supplemental, ERV, the energy recovery. And what we're really highlighting, there are a number of different interacting things that are going to change or affect that climate that single unit is seeing. And more, though, people are saying instead of trying to bring the heat or the cool from the roof, they're going to do some added conditioning of the climate at the end user unit, putting intelligence there. And that's what the whole premise of our ACC-ECM Plus is, to put more smarts, more capability, more function at the end user place, the point of control. Next slide. How do we do that? This small box is put literally under the covers at the individual unit. To date, some 40,000 are installed, mainly in the US, but South America, Canada, and Europe and Asia as well. And it has been used in a variety of applications and systems. So it's not something new or unknown. And recently, we've expanded the name to include the ECM Plus, and actually gotten a rebate acknowledging that. So I know many of you are familiar with ECMs, electronically commutated motors. Well, this also is an electronically commutated motor, but more. It's an adaptive, smart system that electronically commutates the motor. Next slide. Next slide, sorry. Well, how does it do that? In that little, let's say, little 4x5 box, it's like a microprocessor, but it's a microprocessor for power. And it takes in fixed electricity, and you can program with various inputs and outputs how to change, how to adapt, how to make smart that electricity. And what enables it to do that, it will read real-time conditions that are happening. So temperature, humidity, oxygen, CO2, building management system, voltage input 0 to 10, that unit will take any of those various signals. Based on what those signals are doing, it will then take the program and adapt the output power by converting the fixed incoming power into smart adaptive output power to control the units that are in that system. Next slide. So here's an example of a typical fan coil on the left. And what we're showing is that single blue box in the middle is controlling not just the fan above it, which it is, but also, as you notice, it could also be controlling the damper. But how is it controlling it? It's controlling it by taking in real-time signals. So you see the sensor on the top looking at the discharge air. You see a sensor that's looking at the return air. You're looking at a building management system. You're looking at a valve that's there. So multiple parameters are mixed in our box and given directions or program to now give smart or adaptive programmable signals out to the fan or the other units in the system. And what that also highlights on the right there is just what the Aldis and others are doing. Instead of a damper, why not put another fan in? A fan that the ACC can co-control So my outside air isn't just passive or opening, but I can modulate it depending on needs or depending on conditions. And so what we're highlighting is that there are multiple functions well beyond just controlling the fan motor, the EC motor. It's many other things that this box does. Next slide. Here's just another example. Those are patent, these are patent drawings. This has a number of patents on. All we're highlighting here is that in a real world scenario, so many things can be going on. And here, this is a typical air conditioning system, a PTAC, where you have more than a single fan. You have a compressor, you have exiting condenser coils, incoming evaporator. So you have a lot of things happening that are not seeing a constant. When it doesn't see those constants, what can you do about it? We do it because we can get real-time monitoring, blend it in, and then send it out so that we're managing, adapting real-time, changing conditions to the changing needs, but optimizing them at all times. So improving the performance by putting a smart driver, if you would, inside the car or this particular vehicle, in this case, the HVAC vehicle. Next slide. Next slide. Okay, and here's how we kind of do that. If you look on the far left is a flow chart, and this is a typical functioning operation of a fan coil. And all we're highlighting here is before we're in there, there's a sequence of things. Is it calling for heat? Yes, no. If it is, you do this, you do that, etc. So that stays pretty much intact. What we do in the blue is what's in our box, and we just insert it into the loop. We don't disrupt. We don't make the user figure out, oh, I have to learn it. No, we're pretty much transparent to the end user as far as function, but as far as features and comfort, they certainly notice it. And so we just blend in, and although there's a lot in that blue box, it just inserts into the loop and now makes that whole existing loop smarter. So we really have what is called a capability to field upgrade an existing unit without having to modify or alter that unit, just insert our function into that existing unit. Next slide. And what do you get when you do that? Here's an example of the room comfort needs of the end user. They'll set a set point. You see on the left there, that's 72 degrees, the yellow A. And around that set point is a band where the system is going to turn on and off depending on whether it's calling for heat and been satisfied or not. That red sine wave that you see oscillating back and forth, coming on some 9-10 times, is a typical measurement in a room of a room that is targeting at the thermostat for 72 degrees. But if you look at places in the room from your cold feet to maybe your warm head, the temperature varies throughout. And as it does, that's what turns the system on, is saying now it's time to bring that heat up. And then as it does, it overshoots that set point, overshoots the hysteresis, and finally turns the system turn off. So that red cycling is the on and off of the system that the thermostat sees. And that same view here, you'll notice in the band, the hysteresis band, there's a green sine wave, but there's only 6 sine waves as opposed to 10. This is what happens when our unit is inserted. Instead of your system coming on 10 times in a span of time, let's say in an hour's time or 2 hours, whatever it may be, that same system with us inserted into the loop will now come on much less, maybe 6 times, maybe 5 times, maybe 7, but it always comes on less and holds a tighter room temperature. That's what we're really about, improving the occupant comfort. So we do 2 things. we improved the performance. And while doing that, we significantly reduced the energy consumption, i.e., we stop wasting energy that the system can't use effectively. Next slide. And here's an actual energy measurement of what's happened. The last one was just looking at temperature. This is actually looking at the power. And it's a similar chart matching the early one, but now we're actually looking at, for PTAC or wall plug, here's how much energy this system is using. On the left, you see the hundreds of watts of power, and it's cycling on to 9 to 10 times to be able to produce the heating for that room to manage keeping that set point. Holding that same set point, changing nothing else, flicking the switch of our box that has been inserted in, you now cycle on only 5 or 6 times to hold the same set point in that same space. Now you can just quickly sum up and see we're on a shorter time, we're on less time, and that's where kWh, significant amounts of kWh are saved, as well as you see even the overall height is reduced of the run time. Next slide. This unit has been installed in some of all the above you see there. So we're not product specific, we're electricity specific. And so if you're powering something with wall power, and that's the sinusoidal AC power, 120, 240, 280, but if you're powering a unit with electricity, we can take that fixed, dumb electricity, because it's just running, and program it on the fly to react to real world room changing conditions. And so these, doesn't matter what it is, if these are using electricity and fans or standard types of heating, cooling things, we can enhance their performance in the field. Next slide. And this isn't just our viewpoint. This is just an example of what a utility recently went through. New York State and actually candidly Massachusetts followed not long after, where they looked at it and said, this thing improves the motor's function, but they discovered it's improving the system's function. And so this was a heavy calculation that was done by utilities to net out that overall there's some 30% system total unit savings that occurs with the after installation of our box versus its before operations. And that's all we're highlighting here. And now both New York and Massachusetts have put in place a prescriptive measure. If you install our unit in the field, it can qualify for some rebates. And they're still determining the amount of rebates, but it's been approved. Next slide. And just to kind of expand a little bit on that last slide and what you see here, why they're still evaluating it is because our box can go in and run on a fan coil with a 1/20th horsepower motor, and our box can go on rooftop units like this one here, where you may have a 2 horsepower motor. That same 4x5 box will run each of them equally efficient. And you see a range of items on this list here of where the box has been installed and the range of savings. Now, you might say, well, why isn't it consistent? Because the real world conditions are changing all the time. So we're saying when worst case conditions are there or best case conditions are there, we're going to recognize and adapt. And so instead of just only getting 20%, as you see on that first one, when conditions are right, we'll optimize and get 50% more than what it was normally running at before we were in there. And that's where these ranges of savings occur. But in every case you see, no matter what, how bad things are, if it's producing heat or producing cool, you're going to get double-digit savings. And in some cases, over 50%. And this has been documented time and time again. In the next slide, please. Where as you get those savings in the individual fan coils, there's a ripple effect. The sum of the parts is better than waste in the whole, I'll say. And so if you think about 200 fan coils being driven by a chiller on the roof, and all of a sudden those 200 fan coils are demanding 30% less energy, that chiller can actually throttle back to 30% less runtime. And we've seen this time and time again, or the boiler or whatever it is that's providing that source of energy. And so you don't just get the savings with that little box that the individual occupied spaces, which you absolutely do, but the ripple effect is it enhances the overall system performance because it's driving each one of the individual units smarter. Next slide. And this has been confirmed by not just us, but the U.S. Department of Energy, NYSERDA, Environmental Testing Labs, NYPA, New York State OGS, a number of universities all around the country. We don't even have some others in here that have done it. A number of major corporations. All of these names up here are places that have had our units installed where they did exhaustive testing to confirm or disprove whether or not it's safe. All of the above have proven that the same thing, it always improves performance, and as it does, reduces energy consumption, basically energy waste. And the locations, as you see, from hotels, hospitals, motels, museums, libraries, mobile courts, factories, office buildings. If you're doing distribution of heating and cooling, again, where electricity is involved in that process, we're going to reduce the cost of that fuel usage as well as the electricity consumption and achieve the same or better results. Next slide. I'm going to pause here. I should have paused earlier. I don't know if there's some questions and all, but before we get into, quote, what's under the covers of the blue box, we've been really talking about when it goes under the covers of an HVAC box. But so before we go deeper, I'd like to see, are there some questions about what we've covered so far?
So far, Art, there's not any questions.
Okay. And you had mentioned some yesterday, there were a couple that I thought were some good questions about the ECM and the size of the unit, the electricity. So whether it's a 50 hertz or a 60 hertz motor, again, whether it's a 20th horse or a 2-horse motor, the same box can be programmed to operate all the above. And often one program will still work with that range of units without having to do major modifications to the single program. So all we're showing here is that the technology behind it says that we're not only just enhancing the external system performance, which we do, making the system run smarter, we also make the motor itself run smarter. And all we're illustrating here is that if a motor is running a fan versus a compressor versus a pump or an electric heater or a light bulb or a number of light bulb, electric heater or other. In the HVAC system, electricity is being used to do a number of things. But the motor that's usually driving that doesn't know whether it's powering a fan or a brick or a compressor. Wouldn't it be nice for that shaft to know that the load is not the same on a pump as it is on a fan or vice versa? So all we do is, like we said, let's see if we can make the motor smarter by giving it the intelligence on the fly internal to the motor to say, don't just send in a single sine wave that is just being converted into a rotating shaft. Let's go and look at what is that shaft rotating and see if we can now adapt that sine wave to be a vector, a smart vector that says it's going to have smart external rotating shaft motion. Next slide. So we just kind of illustrate here that you know, a motor is producing a rotating shaft. Well, a light bulb just produces light. But you'll see that incandescent bulb on the left, it produces light, but also produces a whole lot of heat and waste. What comes the CFL, it now also produces light, but it produces it with a lot less heat. Why? Because it's doing a better conversion of that electricity into light. And now we think that's what the ECM is, but you see today LEDs, it's also only producing light from incoming fixed electricity, but without a lot of the waste, a lot of the heat. That's all we're doing when we go and add our technology to an AC induction motor. So on the left, you see a PSC motor. In the middle, you see an EC motor. We think the EC motor is a good improvement over an AC motor that doesn't have the intelligence that it could have. And that's what we did. We took our box on the right, added it to the motor on the left, and basically leapfrog the one in the middle. Just like that incandescent lamp on the left, now with the LED has leapfrog and pretty much made obsolete CFLs. We don't think, it's not our goal to obsolete the EC motor, but we think we're offering a solution that's as much of a difference and enhancement as that LED is to the CFL. Next slide. And again, we talked briefly about this earlier. This isn't our singular view. There are utilities with some heavy duty studies, evaluations, customer feedback that all have confirmed time and time again. Install our box. All of a sudden, several things happen. Customers are happier. They see a quieter system, a better performing system, a more comfortable system, and they see their bills go down. And they see it without this creating havoc to the grid. ECMs and some of these other motors, VFDs, they'll reduce energy, but sometimes somebody is paying for it. It could be the bearings, it could be the grid, it could be a nearby system. We do this with clean power. And that little document on the right is just one of several ones done by the Department of Energy, U.S. Department of Energy, acknowledging the validity of our claims and what they themselves verified as to its functionality. Next slide. And I won't belabor this. This again is just a comparison of like how our adaptive photonic controller matches with a VFD, which matches with an EC motor, and all of them kind of doing the same quote work. In what are the varying results, doing the same work with how much is pulled from the line versus how much is delivered to the load. Next slide. And this is just saying, looking at those three things very quickly. The blue represents the a PSC motor, standard off-the-shelf motor, coupled with our box. The middle in orange is an EC motor doing a similar size work with a similar size motor, and the gray is a VFD working on that same PSC motor. And you'll notice in the very next harmonic there, we're all the way down to like under 20%. They're still pushing 80%. What does that mean? That's energy that's got to go somewhere. Where's it going to go? It's not going out to the shaft. It's going out to the windings. It's going out as heat. It's going out as reflections. And they're at the fifth harmonic, the seventh harmonic. We're virtually non-existent. And they're still pumping out this energy. That's why these units will run hot. That's why they need fans. That's why they need cooling. And yet, there's still harmonics there, as you see out to the 29th. With guess what? That's the EC motor, a DC motor. So what we're highlighting here is there are other benefits besides the performance, the energy savings. There are some system benefits when we install our unit in there. Next slide. And we could get into why. This is just, again, talking about how others slow down motors. And I don't care if it's an EC, DC motor, a VFD driven motor, they all pretty much are using pulse width modulation. And it's a good way to manipulate data. It's a good way to use for computers and processing, but digital switching is not so good or friendly or the best with power. But it does work. And on the far right is really what the premise is, that you see those rectangles, those square waves. And on the top is basically the time that the unit is on, with how long is the cycle on. And the longer it's on, the more power is being delivered to the motor. The shorter it's on, the less power it's being delivered to the motor. And as it does, that's what slows the motor down or speeds it up, is how much power is that motor getting. But those nice looking clean square waves on the right look more like the ones on the far left. There's overshoot, there's ringing. And if you look down below that on the left, that's what the current looks like, a haze. That's what the motor is trying to absorb. And if you look at that thing in the middle, that sine wave's got all those little fuzzies on it. That's as the motor is trying to absorb all that stuff on the left. Next slide. Instead of doing it, we take the same incoming sinusoidal power, the blue, and the current on the PSC motor is what's being illustrated here, taking that exact same motor and now coupling it to our box. We go and change that sine wave into a vector, and we also move the current so it's under the curve. So if you look at a voltage current relationship, i.e. the power factor, you'll see that we enhance and bring the power factor closer to unity from high to low, and we give the motor, instead of this sinusoidal wave that is still lingering around after you've reached your saturation point, you know, all the electricity is doing, it's creating a current, which in turn is creating a magnetic field. Well, and that magnetic field is creating, it's creating a flux that creates a magnetic field. But once it hits its peak, that's it. Now it reverses, and it's going to try to reverse that field. We get out the way and say, you don't want to continue to have that current flowing when there's no need for it, because now you're going to just continue to burn up power, generate heat, etc. So we could get into it, but all we're saying is this is some of the technology that enables us to run a motor without the heat, the cool, without the harmonics and the noise and some of the other things. Next slide. Some other features the box has is a soft start. Won't get into, but the idea is just quickly, when you think of a PSC motor, it's a big hunk of copper until you get it moving. And so when you plug it in, you may see the lights dim because it's a short. It's literally a dead short when it's first turned on. And that's why you get that surge, an inrush. And that's why they have staggered on time. But anyway, the point is that we take that same dead short and no, we add smarts to it and say, don't go and send full power rushing in when the motor is not spinning yet. Let it get up to some motion, and we just delay it enough such that we're creating magnetic field, so that we're creating resistance, so that we're diminishing the inrush current and giving that motor some smarts again. And so the one box you see on 3 different fan sizes, the one on the far right there, the spike is so high you couldn't even fit it on the same page. But you get the idea of like, we reduce kWd as well as kW and kWh. Next slide. And I guess I should pause here because I don't want to delve down too deep, but this is a typical picture of or plot of the torque and the horsepower on the left, torque on the right. And you'll see a typical PSC motor, independent of eclectic or Arterm or whatever. A 3rd horsepower motor has the potential to go all the way up to like 2x its power, as long as you don't go over the nose of that curve and tumble down into stall. Because we have the smarts, we're constantly monitoring where the slip is, where the motor is, what's happening, and thus we can move up and down that curve and optimize torque and optimize horsepower, but not cause problems to the motor while doing it. And that's all we're highlighting here. So we'll move on there because probably. And we do that because we don't just take a 2D slice, which everyone sort of does. When you see a motor curve and you look at the motors on your fans and everything, you always see kind of this 2-dimensional curve. A motor's not a 2-dimensional functioning vehicle. It's a multi-dimensional. We live in a 3-dimensional world, not 2-dimensional. So our technology says we really need to do this on a 3D plane, a 3D area function, not just 2D. But because the world is using 2D for most of their motors, we'll take slices out of the 3D plane and say, we'll program this into that motor. So depending on what it is, we'll mimic what's there. But if you really want the smarts, we can go and push it into the 3-dimensional plane and operate it a lot more intelligently and a lot wider range. Next slide. More of the same in some of the technology, but just quickly, that equation down in the middle and the bottom there, this is what an AC induction motor actually needs to function. So it's not just voltage and frequency, okay? You have slip, you have reactance, I'll call it, but the basic inductance, resistance, and all these parameters interact at different ways, at different frequencies, at different magnitudes, and at different loads. And so you have to kind of factor in these, well, you don't have to, but you can factor in these things and say, how can I optimize the motor to be able to look at these multiple parameters to then extract the maximum torque or horsepower or speed, or what is it I want to extract out of it, and manipulating those equations, you can go in and walk the surface of that curve any way you want on the right. Next slide. And this is just saying, because the box doesn't just work on the motor. So for instance, you see the motor RPMs on the vertical y-axis, you see on the x-axis their temperature. And so there's a curve that says the motor RPMs can follow temperature. But if you want, that same motor can also be using our box blended so that the electricity is being influenced by not just temperature, but by, say, humidity or pressure or some other parameter that you want to map in for the motor to react to concurrently as it delivers its power out. And so that's that 3-dimensional approach that we talk about, that we do. And it's more than 3-dimensional because it doesn't have to be a static or a single third parameter. Next slide. But we take 2D slices, like we say, because that's what everyone pretty much works with, and that works. And so we're just showing here that the 3-dimensional curve that we just showed, you can take different slices out of it. So if you want a certain temperature, certain pressure, next slide. We can program them, and within the boundaries of what the unit is that you're working with. Is it an air conditioner? No. Is it a freezer? No. Is it a refrigerator? No, it's a furnace. Okay, well, it has a different profile than the other. But depending on what it is, we can create a different profile and to optimize it. So that fan knows if it's in heat mode versus cool mode. It knows if there's a return air that's cooling it down, or outside air that is overwhelming the coil. So these are all the things that we're able to kind of program in to give it the smarts to react. Next slide. And pretty much we're wrapped up. So these are just examples of programs. Right now, the box can take, when I say can only take, it takes up to 4 active concurrent programs in that aftermarket box, because most people don't want to control more than 2 or 3 things anyway. And so we have up to 4 that you can program in, and we'd have to know if you're not going to take one of our standard programs, we can tailor it to what that last slide showed. So I pretty much like to wrap up here. I'm hoping for some more questions there. Go ahead and.
Yep, Art, we have a question here. And how will it work on electric stoves? And the list of applications we have, it has a small fan with heating elements. How would the ACC work with that?
These are some good questions. We need these kind of, very well, in an electric stove. Yes, in fact, because you can kind of tandem, or if it's working on electricity, both the fan and the electric heater in the stove can work concurrently together. In fact, you saw in the PTAC patent drawing, in there, one of the things we operate is the electric heater, as well as the indoor or outdoor fan. And we have taken electric stoves. In fact, one still sits in my factory where we were baking some PCB boards, and we were trying to get a very good furnace. And we were able to take an electric stove that varied, if you set it at 400, it would go down to like 350, 325, up to 450. When we put our box on there, we held that same temperature between 410 and 390 when we set it to 400. And you could also set it to 200 or 100. Hope that answered it. I think we can, yeah, we'll stop here. So if there are other questions here, the rest of it just gets into the technology. The whole thrust of what we'd like to encourage you is that if you're using any of those types of HVAC systems, fan coils, water source heat pumps, VAV boxes, and so forth, the whole world is singing ECM motors. And it makes sense because they do save some energy, but they have their challenges like everything. And we're highlighting that if you are also using AC induction motors, don't throw away the baby with the bathwater. We're saying we can take those same AC induction motors and enhance their performance, and we'll say on a par with the ECM, and even more so. In fact, that's why the utility has allowed us to rebrand and call adding our box to a PSC motor, an ECM qualified motor. So next time you're looking at an application that's, oh, you got to have an EC motor, think about a smart, adaptive ECM Plus solution, not just motor.
Hey, Art, we have a couple more questions here.
Sure.
One is, can these be easily installed in existing equipment? And with that, are the controllers installed within the equipment or remotely?
Generally, first, yes, in a word, yes. Those 40,000 units, in most cases, were installed in working field systems and put under the covers. That's why the box is kind of the size it is now. Can you put it in everything? No, we've had to put on the outside of some PTACs, you know, where they didn't have room. But generally speaking, it'll go under the covers, and it essentially just goes in series with the incoming power. And then coupled onto our box are sensors that now go and do what it is you want it to do. So if it's a temperature or is it airflow? So we just interrupt the incoming power and say, okay, we're going to take this fixed incoming power, and now our box is going to tell the system what do you want on the outgoing power. So we'll modulate to match the temperature, or modulate to give certain pressure, or react to humidity. But the premise is that in most cases, people are focused on temperature. And so a lot of the standard profiles are already set up for heat and cool temperatures that allow you to just plug it in, and you've got a smart solution to a previously dumb or fixed speed PSC motor. Probably rambled too much. You said another question there?
Yep. How does it work for fan-powered VAV boxes?
Well, depends again on what you want to do. This is kind of the plus and the minus. We've had customers that just wanted to have a dial on them. We've had other customers that wanted to monitor pressure. And we've had other customers that wanted to look at the temperatures that were there. So it depends on what you want to do. And some of them said, oh, we want to hold a certain a CFM. So what is it you would like? If you tell us that, yes, we can go into that existing VAV box, series our unit with it, and then plug in sensors to it that will allow it to do what you'd like it to do. And tell us what it is, and generally we can adapt the sensor to do what you want, the box to do what you want. And if that's not, if I'm not answering it, please, thumbs up or thumbs down or boot.
Well, thank you, Art. Doesn't look like there's any other questions. If y'all do have any other questions, feel free to reach out to us at Buckley. We can answer or make sure to get a hold of Art so he can answer your questions.
Yeah. And I'd like to just mention, Mike, too, we appreciate this is kind of a fire hose, I know, it's a lot here. And what Buckley has been trying to do and what we're trying to do is just kind of whet your appetite and make you aware of the fact there's an alternative out there that has been tried and tested and works. And it's been installed where people have put them in California. They put in tens of thousands on a rebate program there, where they got it down to a half an hour installation from walking in the room to walking out. And they end up with this smart system. So that gives you some sense of how easy it is to install, even though it's a very powerful solution.
Very good. Art, thank you very much. Pradeep, thank you for the slides. Hey, Pradeep, do you mind putting on the very last slide that has our contact information on there,
Sure,
please?
yeah.
Again, thank you, Art. Thank you, Pradeep.
Yes, thank you, Mike.
Yep. I hope everybody has enjoyed today's webinar and got some useful information out of it. I do want to mention real quick about Buckley. We deal with these type of systems every day, and we have over 10 mechanical engineers supporting the Northeast market for design and application support on this product and all of Buckley's other products that we represent. If you have any other questions that you didn't think of on this webinar, or please reach out to myself or your Buckley representative. If you're not sure who your representative is, get a hold of Sherry. She'll get you in the right direction on who your contact info is, and we'll be glad to help you in any way. Not only do we support the engineering or the application or sole solution at Buckley, our service department is also certified on all of our products so that they can diagnose, do a startup, commissioning, anything that you really need with the products that we manufacture. So again, I want to thank everyone for attending. We appreciate your time, and please feel free to send out any questions that you might have. And we appreciate you, and I hope you have a great day.
Thank you.
Thank you.